Welcome to my channel, Tech Lounge.
Hello, colleagues. We are here with a new FreeCAD 1.1 video. Today, we will analyze the strength of the system you see on the screen under a 10 kilograms load using FreeCAD version 1.1.1. We will see in which direction and how much our material will flex, bend, or whether it will break under this load. We will also analyze the risk level of this amount of deflection and bending. First, we will quickly draw this part in FreeCAD. Then we will move on to the analysis phase. The part we will draw consists of a square flange with 10 centimeters sides, mounted to the back of a 40 by 40 square profile with a wall thickness of 2 millimeters. The length of our profile will be 20 centimeters, fixed from one end and free at the other. In technical terms, we will draw a cantilever beam and then analyze it. Let's get started. As usual, we start our drawing with a parametric body. I am switching to sketch mode. From here, I select the XZ plane. In sketch mode, from the right side, I activate my rectangle tool and then the rectangle from center tool. Right from this center, I'm drawing a 40 by 40 millimeter square. Without changing my drawing tool, I continue with the same tool. This time, again from the center, I draw a 36 by 36 millimeters square. This way, I obtained a square profile with a wall thickness of 2 millimeters. I click Close, Exit, and extend it using the Extrude command by 200 millimeters, which is 20 centimeters. Our profile is ready. Now I turn to the back side of this profile. I orient the rear view facing me, and by clicking on the wall thickness, you see. I create a sketch on this face. With this created sketch, again starting from the center, I draw a 10 by 10 centimeter square for flange. And I click Close to exit. I select Extrude. I turn this into a flange with a thickness of 3 millimeters in the direction shown. Yes, our part continues to take shape like this. We have one final operation left. We will drill a small hole at the tip of the part. This hole will be where we suspend the weight. I click the bottom surface of the profile and switch to sketch mode from this face. I bring the part towards me a bit and zoom in slightly. I will drill a hole on this surface. I select Circle tool. Since this axis is right in the middle, I draw a small 3 millimeters hole right here on my part. Or rather, I define a 3 millimeters diameter circle for the hole. Next, I want this circle to be 1 centimeter away from the tip of this profile, but can't catch that edge. To reference this edge, I need something different. I click the external geometry icon up here. Then click the edge. Then I click the dimension tool and set the distance between the edge and the center of the circle to 10 millimeters. Yes, now it's offset 10 millimeters from the tip of the profile. I am done here. I use the pocket command to cut in this direction. As our wall thickness is 2 millimeters, the default value of 5 millimeters for the pocket command is OK. I click OK, and we have created the hole this way. Although they won't be included in our analysis results, to ensure a more realistic appearance, let's drill 4 mounting bolt holes on the rear flange. I click the front face of the flange. I switch to sketch mode. I select the circle drawing tool. I'm drawing a 5 mm diameter circle roughly around here. I want this circle to be 1 centimeter away from both the top and left edges of the flange. For this, I click the external geometry tool. As before, I add a construction line to both edges of the flange. Then I select Distance Dimensioning tool. I set the distance between the center and this line to be 10 millimeters. Similarly, I set the distance between the center and this line to be 10 millimeters as well. Then I select my circle. I activate the mirror command. I select this axis to mirror the circle. Look, on the right side, it created a symmetrical copy relative to this axis. Now I select the right circle. I clicked mirror again. This time I select this axis as the mirror axis. I select first circle once more. I activated the mirror command again. I selected mirror relative to this axis. Thus, 4 symmetrical circles were created relative to the center. I exit from here and create the 4 holes using the pocket command. I'll just leave the default 5 mm value as is. Now we are ready, the FEM analysis. We switch to the FEM workbench and start our analysis. At this stage, the first thing to do is to click on the new analysis icon represented by the letter A in the top toolbar. If you cannot see it here, New Analysis in the Model menu is the menu item that performs the same function. I click it, and as you can see, a new item named Analysis has been created in the feature tree on the left. The next step is to define the most important piece of information for the analysis we will perform. This information is the type of material. We know that the behavior of the material under load directly depends on its material type. In other words, we need to specify whether our part is plastic, rubber, composite, steel, aluminum, iron, brass, wood, concrete, glass, or any other material. To assign a material, while the analysis container is selected in the tree view on the left, I click the solid material icon on the top toolbar. When I click the arrow in the drop-down menu on the left, all the built-in FreeCAD materials are listed one by one. But before making a selection from this list, I'd like to mention an important issue with some of the materials listed here. At first glance, it seems there are many material types available here. However, when you look at closely, you'll see the same material names listed under different categories. So, why are there duplicate names? For now I am exiting with cancel without assigning anything. If you pay attention to the tree view on the left, there is an object called Solverx Tools at the very end of the list on the left. Keep this in mind. Now I click the solid material icon again. This is the exact same list as before. When I select any material from here and click OK. For instance, I selected aluminum right now as an example. A new item has been added here. This item holds our aluminum data. However, I think I have selected aluminum right now. But look, when I click on this aluminum item, we see that all the values displayed here are 0. If we continue our FEM analysis this way, we won't get any results from it. Therefore, we need to overcome this issue. The most solid first step in solving any issue is finding out where it comes from. And that's exactly what we're going to do here. First, I delete this faulty material definition object in my tree view by pressing the delete key. And I move on to the material assignment step again and expand my list. If you pay attention to this list, you will see that there are various categories here. For example, there is a folder named Appearance, and there are many materials under it. Continuing through the list. Down here, there's a folder called Machining. Underneath it, a lot of materials are listed as well. There's a folder called Patterns. Under that one, different materials appear too. It continues like this. Some of the folders you see here have absolutely nothing to do with the FEM analysis we are going to perform today. These are categories for different purposes, not for FEM analysis. For instance, this appearance folder in the list you see here is a folder that holds visual coding and color information of the material. Continuing further down. For example, there is a folder called Patterns. Underneath this, there are various materials as well. You can see them right here. This folder is a separate definition classified by technical standards for coloring of technical drawings or architectural plans. Scrolling through the list. This machining folder holds cards containing the machining parameters required for machining operations. None of these are relevant to the FEM analysis we'll be doing. Now let me be the one asking the question on your mind. If these categories are not for FEM analysis, then why do these choices show up in the FEM materials list? This is a topic that is still heavily debated on various forums and hasn't been conclusively answered yet. I have some guesses on this matter as well. But to avoid straying from the main topic of the video, I don't want to include them here. All we can do is double-click on the material object in the tree view on the left after making a selection, and check if the parameters show up as 0. As you can see right now, for the aluminum I selected, they have come up as 0. This means that I haven't actually selected something from the correct category. I exit and open the material cards list again. Now I will find aluminum from a different folder here. Look, there are aluminums here. There's a card listed as generic aluminum. I click on that. And then click OK. I double-click on the material object in the tree view on the left, and the values appear here. Now I have selected the correct material. I click OK to finish this step. The next step is to define to the system which end of this part will be the fixed end. Since our part will be mounted to a wall by its flange, we'll define this flange as a fixed support. The command I will use to define the fixed end of my part is the fixed boundary condition command shown right here on the top toolbar. If it is not visible here, alternatively, you can access the same command from the model menu, under Mechanical Boundary Conditions and Slot section. I click the command. I click Add from the left panel. I rotate the part. I click the back face of my flange. The name of the back face of my flange appears here, and I click OK. As you can see, a new item named Constraint Fixed has been added to the tree view. At this point, we need to clarify something. Since we drew our part within a single body, from FreeCAD's perspective, this is not an assembly of a separate flange and profile. This is a single solid part. What this means is, since the analysis we will perform targets the material's strength under load, details regarding how the profile is attached to the flange and the quality of that connection are excluded from calculations. In other words, the joining method, whether glued, welded, or fastened, is not considered in calculations. Workmanship and connection defects are also not considered in calculations. Likewise, the mounting type to the wall, such as bolt or screw sizes and types, is not considered in the calculations. Besides, the wall type such as concrete, metal, or plastic, and its thickness are not considered in the calculations. We could easily expand this list with similar assumptions. When we define one end as fixed, FreeCAD considers it to be an ideal and perfectly rigid support, no matter how it's actually built. So in our case, the rear flange is treated as a perfectly rigid support. The next step is to apply the load to the front hole of our part. To do this, we'll click the icon right next to our previously used one on the toolbar. When we click it, a set of icons will pop up. From there, we'll select Force Load. If you think you'll need these often in the future, you can drag the icons here like this to keep them accessible. I begin operations by activating the Force Load command. A panel opened on the left. Now we will specify to FreeCAD that the front hole of the part will be the location where the load is applied. To do this, I first click Add button on the left, and then select the inner wall of the hole. As soon as I select it, the name of the surface appears on the left panel. However, if you notice, the arrow direction is currently pointing to the right. This indicates that the load would act on my part as a push from the left. That is not what I want. I want gravity to act along the vertical axis, so I need to make the arrow parallel to the vertical axis. In FreeCAD, we can easily define force directions by referencing existing geometry instead of entering complex vector values. To make the arrow parallel to the vertical axis, I first select any vertical edge on my part and click the direction button on the left panel. As you can see, my force direction changed. It looks okay, but it's not. As you can see, it's inverted. By clicking reverse, I adjust the direction of my force toward the desired orientation. So now, the load will act from top to bottom, meaning gravity is directed just as we need. The last step I need to perform is to enter my weight here. Since my mass will be 10 kilograms, I define my load as 9.81 newtons times 10, which equals 98.1 newtons, and click OK. As you can see, my load has also appeared as a separate element here in my tree view on the left. The next step is to mesh the part. Since continuing without knowing what mesh means would leave the tutorial incomplete, I'd like to quickly summarize it without going into too many technical details. FEM is an abbreviation that stands for Finite Element Method. Just like in our part, analyzing systems made up of various geometric shapes and structures as a single whole is nearly impossible. Instead, it is necessary to divide the part into small and simple finite elements, like triangles, cubes, or pyramids, and solve each section separately, and then aggregate these solutions to reach the total result. This process of dividing into small and simple elements is called meshing. In the meshing process, the smaller these elements are, the closer the final calculated result will be to reality. However, as these small elements increase, the matrices generated in the calculations also reach massive sizes. In such cases, your computer's performance and RAM capacity are of great importance. In this tutorial, we will leave the element sizes in the meshing process at the default settings determined by the FEM module. These settings are quite sufficient for basic daily analyses. However, if desired, we can also define this element size ourselves in the FEM module. To subject the part to the meshing process, we will use the command group shown here on the toolbar. To see the icon group here better, I drag and drop it right here. As you can see, different commands are available for different meshing operations. Two of these are FEM Mesh by NetGun, and right next to it FEM Mesh by GMSH. These are the two most commonly used methods for finite element analyses. To start the meshing process, I select my part, which is the latest object in the tree view on the left. Then I activate the second of these mesh types, the FEM Mesh from Shape by GMSH command. A panel like this opened on the left. The maximum and minimum size values shown in this panel are where we will define the mesh element sizes mentioned earlier. If we leave these values unchanged as 0 and click Apply directly, the meshing process will be performed according to its own default values. Without changing anything, I click the Apply button and wait. And the meshing process is complete. I click OK and exit. It took 7 seconds for my part with default mesh size setting. Let's align our part directly in front of us. This way, we can see all of it. Everything is ready. Now we can move on to the calculation phase. The solver module is this element shown under Analysis in the tree view on the left side. I double-click on it. A panel like this on the left appears. In this panel, make sure that Static is selected under the Analysis type options. Then I click the Write Input File button. After waiting for a short while, a message like Write Completed will appear. Right now, FreeCAD has created a file in the background containing all the necessary data to perform the analysis. Next, by clicking the Run CalculaX button, I tell it to start the calculations. I don't know if you noticed, but right now, we are facing an error. Look, in the lower left window. It says CalculaX started running at 0.1 seconds and stopped within 0.1 seconds. This is not a normal situation. It shouldn't have been like this. I know the cause of this error, and now I will explain it to you. Before that, how I access this information is a subject as important as the error itself. Log records are always king. Now from the top menu bar, let's follow the path. View, Panels, and then Report View. Look, a window opened at the bottom. This window shows the operations performed in the background and errors raised while FreeCAD is running. If you wish, you can keep this window permanently docked here while working. However, because it creates visual clutter, I prefer accessing this window only when I need it. I'm sure we'll find the culprit right here. I think I got it. If you pay attention to the bottom lines, it shows us right here what error we encountered. I close the Report View window and focus on the file path shown right here. Because the file path here is in Windows abbreviated file path format, FreeCAD cannot see this folder directly. Furthermore, it is also a problem when the file path contains symbols outside of standard English characters. To overcome this issue, a simple file path would be enough. I click 3 dots on the right of the path and navigate to Windows C root drive. And create a new folder here named FreeCAD Test. I click Select Folder and define this folder here. Now I click the Write Input File button again to ask it to prepare the necessary file for calculations. As you can see, it took only 1.5 seconds and completed without any errors. Everything is properly set up for the analysis. I rerun CalculaX for final calculations. It is running right now. After 1.5 seconds, it showed me here that it completed without any errors. I click Close to close this panel. Since the calculations are now finished, let's check the results to see if our model is safe under a 10 kilograms load. So, how will we do this? In our tree view on the left, we see that a new element named CCXRESULTS001 has been added. It's a container object that holds all the calculated results. I double-click on it. Before evaluating the panel opening on the left, let me share a few pieces of information about the view on the right. The light and dark gray areas you see on the part indicate regions where minimum stresses occur, meaning these are the regions almost entirely unaffected by the load. Light and dark green parts indicate medium-level stresses. Yellow and orange regions show high-stress areas, and red regions show maximum stress areas. When we examine our part by rotating it slightly, we see mild orange-colored stresses on the vertical walls on both sides of the hole. Other areas have significantly lower stresses. Now I orient the front view of my part towards me. I tilt it slightly downwards. As can be seen, we define the direction of force applied by the load in this manner. In other words, we define the direction of gravity in this direction. Therefore, we expect our part to bend downwards under this load. When we look at the axis view at the bottom right, gravity appears to be along the z-axis relative to our part's orientation. Therefore, the up and down movement will take place along the z-axis. Now let's focus on the left panel. The displacement x, displacement y, and displacement z options show the amount of bending along each axis. I'll select displacement z, since gravity acts in this direction, as mentioned earlier. This may vary for you in your other drawings. Since we drew the part centered at the origin point, a negative z value indicates downward deflection, while a positive z value indicates upward deflection. We observe a downward deflection value on the order of minus 66.5795 micrometers. This value roughly corresponds to 1/15 of a millimeter. You might ask why we see a deflection value in the positive direction, that is upwards, while the load pulls downwards. As the material flexes downwards, the edges deform at the same time. The part elongates, and concavity occurs on the top edges. For this reason, upward elongations can occur. However, looking at the value on this part, the 17.3179 nanometers value we see actually corresponds to approximately 1 in 60,000 of a millimeter, meaning it is practically negligible. We continue examining the panel on the left. The show option you see here is a section designed to show the part's deflection in an exaggerated manner. By increasing this value, we can simulate how the displacement takes place on our part in an exaggerated manner. As we move the slider, a real-time simulation is displayed on the part, as shown here. Since the system we set up exhibits deflection on the order of microns under a 10 kilogram load, looking at these values, we can say that our part is safe for this load. However, we are not done yet. We also need to check the von Mises stress values. While the analysis we just did shows in which direction and how much the part bends, the analysis we will do now tells us whether this amount of deflection will cause the part to break or permanently deform. To perform this analysis, I click the von Mises stress option on the left panel. The yield strength value of the aluminum material we selected is 240 megapascals. In this analysis, the maximum stress value our material will be subjected to is approximately 45 megapascals, as seen on the screen. This value is about 1/5 of the material's 240 megapascal capacity. Generally, including safety tolerances, values of 2 and above are considered safe. For this reason, we can comfortably say that for this load, our material will not break or undergo deformation, meaning it is safe. At matweb.com, you can find the yield strength and all other technical parameters for the materials in your design. Now let's see what the situation would be if our weight were 100 kilograms instead of 10 kilograms. But don't worry. Since our infrastructure is ready, we will see all the results in front of us within a minute with just a few clicks. I close this screen by clicking close. I double-click on the constraint force element where I define my load. From here, I change my load to 981 newtons, meaning 100 kilograms. The load is applied. I click OK. Then I go to the solver element. Click it. I click Write Input File button. I click Run Calculax. The process is completed. I click Close and move on to examining the results. I click Results container on the left. As you can see, the deflection along the z-axis turned out to be 6,658 millimeters. That's more than roughly 6.5 meters. And as you can see from the view on the right, the situation is not good at all. Now let's look at the failure analysis. I clicked von Mises stress option. Our material, which withstands 240 megapascals, is currently subjected to an incredibly high stress level of 4,464 gigapascals. With these results and the view on screen, it is certain to fail. In short, the structure we built with this material is by no means suitable or safe for this 100 kilogram load. When we applied a 100 kilogram load to our structure, the calculations gave us a stress value of approximately 4,464 gigapascals and a deflection of 6.5 meters. For a 20 centimeter part to flex 6.5 meters is physically impossible. The most important engineering lesson we should take from this is linear analysis solvers do not know that the material will break. According to mathematics, as you multiply the load, it simply multiplies the result. This result clearly shows us that the part has far exceeded its yield limit, has suffered total failure, and that this design cannot be used under this load. And with that, we have reached the end of this video. I hope I was able to be helpful. Please don't forget to subscribe to my channel, like, and leave a comment. Take care of yourselves. Goodbye.
Tech Lounge.